How can we extract information from a series of pictures of ultracold atoms? Do we really get all the information if we fit some average image with an a priori model function? Or is there more to get from the shot-to-shot fluctuations? Let's focus on a specific system, namely a cloud of trapped ultracold atoms. We produce a two-dimensional quantum Bose gas in an anisotropic harmonic trap. We excite the system by displacing the trap center and changing its shape. The gas is out of equilibrium, and we observe the subsequent dynamics by in situ absorption imaging taken at various times. What information can we get from these pictures? We expect that several excited modes of the interacting gas will be populated simultaneously. How can we describe the dynamics of the atomic cloud? Is there more in this series of images than what the naked eye can see? Can we have access to the excited modes? Principal component analysis, or PCA, can successfully address these issues. PCA is a statistical method, widely used in astronomy or biophysics, that can be adapted to the problem of the ultracold atom dynamics. It then allows to identify the vibration modes which are populated directly from the correlations between pixels of a series of images.
PCA proceeds as follows. We first compute the correlation over the entire set of images between two pixels I and j. The covariance matrix elements are the resulting values Sij. We then diagonalize this matrix. The first few eigenvalues account for most of the variance of the full initial sample. The corresponding eigenvectors are images called the principal components. Each image of the initial sample can be recovered as a linear combination of the mean image and the first few components, which are statistically independent.
Let's go a step further and identify the components. The first two components describe the center of mass oscillation along the two trap axes. The third one reveals the shot-to-shot atom number fluctuations. The fourth component, with its four lobes, is the signature of the scissors mode, where the elliptic cloud oscillates around its long axis. Notice that the higher order components identify various sources of noise, like background fringes. This is great, because we can now filter those out.
From a scalar product between a given component and the images of the series, we have access to the time evolution of the weight of this component. For example, the projection onto the first component exhibits oscillations at a trap frequency. The fourth principal component presents a more complex time evolution. It is related to the hydrodynamic behavior that arises from interactions between the atoms.
The first few principal components seems to directly reflect the first excitations. This is confirmed by applying PCA to some simulated data that mimics the experiment and comparing the principal components to images of the exact low-energy eigenmodes. We find a 98.5% overlap between the four lobe components and the exact scissors mode. To summarize, PCA is a powerful tool for getting the best out of cold atom absorption images. It is quick and simple. It can efficiently identify the elementary excitations of the quantum gas. We believe that this method could also be successfully applied to other dynamical systems, as long as they are in the linear response regime, in particular to study trapped ions vibrational modes.